So yes, a lot of words, a lot of technical terms and stuff like so. Our next task is actually to build a face recognition example or project on real data. Real data means the data that is the real faces of humans that is collected and available. The data is available, and through Scikit-learn we will see how to import that data and stuff like so. But let's go through a hands-on example for face recognition. By face recognition, the project will be in a following way. The end result is given a face image, for example. We want to identify whose face is this, so we want to identify the identity of the person. That's the face recognition example. That's a face recognition project that we're just going to do. Another kind of project that might be face detection. So one may confuse this face detection with face recognition. Face detection is a different project, a different module, normally comes under the computer vision, that given an image, detect or crop all the faces in the image. For example, this face, or maybe a bigger face, maybe a smaller face. So crop all the faces or detect all the faces. But we need not to detect the identity of any face, just pick the faces. So that is called for example, just like object detection, where the object is your face. But face recognition actually inputs the face image, may be cropped by a face detection algorithm. But once the face image is available, we need to identify whose face is this. So let's go to our friend Jupyter Notebook and go through this example, this kind of fascinating example. So yeah, let's go to Jupyter. Yeah. So first, let's import certain packages that we may need. What's the best zoom level? Let's say this is okay. So let's import some packages. Maybe we need NumPy. We always need NumPy, so we import that. Maybe we need matplotlib for plotting some data, so let's import matplotlib as well. Matplotlib.pyplot as plt, and maybe we need something from Seaborn. If nothing, then layout at least, but maybe some plots as well. So yeah, so that's the basic packages. I guess we should import these. These normally are always needed. Further, we may set the sns.set. We may call that just here, just to set the layout for Seaborn. Okay, next we import a face data set from Scikit-learn. If you have internet connection, it should just go to the link and it will import the data. And if you have already imported data somewhere earlier, it should fetch that data from there. So there are some real data sets available in Scikit-learn package in Scikit-learn sklearn.datasets. So let's import some face data. Let's import fetch lfw people. This lfw people, that's a function. We are going to import that function, this fetch lfw people, that's a function. But when we will call that function will help us giving the data. So let's import that, import happens. Let's say faces, or let me call it, okay, faces is, let's say, fetch lfw people, and let's say I want to fetch all the people, the data of all the people with minimum faces per person. Equals to 70. Let's say I want to get all the data with all the faces, with all the data with minimum faces per person is 70. See, in this data set, there are a lot of persons. Some persons have, let's say, 20 images. Some persons have 25 images. Some persons have 70 images. Some persons have more or less and stuff like so. Let's say I just want to pick all the data, all the faces or the people, having minimum faces, at least 70, maybe more than that, but at least there's that much. Just you can change this parameter and just go with. So yeah, faces are loaded. On your computer, maybe this take a while. I have loaded these. I have loaded this data set earlier as well, so this actually stays in my cache or memory or hard disk or somewhere. So it fetches from there. If you fetch this first time, it may take some time because it will download it from internet. And once downloaded, then next time whenever you want to access that, that will be accessed very quickly. So it may take a few minutes, for example, to just fetch this data. So don't worry if you call this function first time. It may take some time. That's okay, perfectly okay. Okay, let's see what this faces has, what kind of attributes are there. So there is a data attribute, there is a images attribute, there is a target attribute, there is target names attributes. Let's go to target names, for example. What's that attribute? So our targets are Ariel Sharon, Colin Powell, Donald Rumsfeld, George W. Bush, and all these. How many are these? So let's check in our data set how many classes are there. See, each person is a class. Each person is a class. So how many classes are there? And for each class, there are several data points available, which are the images. I will just show you in a few minutes. Faces dot target names. How many are these? So there are 7. There are 7, and all of them are encoded by Ariel. And there may be target, which is in the form of, yeah, so 5, 6, 7. So rather than playing with the target names as strings, the labels are just encoded as numbers. For example, class 5, class 6, class 3, and all that. And these numeric kind of labels are required for machine learning, because we have to incorporate that label in our cost function, have to compute the cost and stuff like so. And normally these cost functions, they are applied on numeric data. So let's see, for example, what are these? So let's say np.unique faces.target. How many are these? So yeah, so class 0, class 1, class 2, class 3, class 4, 5, 6. So there are 7 classes starting from 0. These are the targets, and all of them, they are just repeated. Okay, let's see some image. For example, faces.images. Let's see, for example, image of the very first person. Let's say plt.imshow. Let's see what that is. So yeah, so this is the first image, and the target of that image, what's the target of that image? Let's see that. Print faces dot target names at 0, for example. So that is this. Yeah. So that's Ariel Sharon. We can have this fancier plot. For example, if we don't want this grid to appear over there, we may have color map that is grayscale. For example, let's say CMap equals maybe a different color map rather than this one. In that case, it will be shown as grayscale. We can remove these grids and all that stuff. But I will just show you. I will just show you by just displaying more faces in front of you. But let me just see the dimension of this face. What are the dimensions and type and all that stuff? For example, type of. Let me just see the dimensions. Faces dot images. Let's say the first image or any dot shape. What is that shape? The shape is 62 by 47. which means that's a matrix with 62 rows and 47 columns, or it's a two-dimensional array with 62 rows and 47 columns. How many total, so that image basically is how many total numbers in there? These are all the numbers representing colors. How many are there? 62, asterisk, 47. How many features are there? Because each, so 2914 features. Yeah. So that means, so what I'm trying to say you is that given an image, for example, if an image is given to you, this image, and that image is, for example, 62 by 47, then you 47, then you have, for example, this row with the 47 numbers, then this row with 47 numbers, this row with 47 numbers. So total, each and every number is actually a feature. So one way is to prepare the data in a vector form is to just pick the first row, that's 47 numbers, place them here, then pick the second row, place them down there, pick the third row, place them down there, and build a vector, for example, maybe a column vector of length which is 62 by 47, which is 29 by something. Or maybe you can build a whole matrix, for example, you can build a whole matrix with the first face which is flattened down, which is the first face is flattened, then the second face is flattened, then the third face is flattened, and this is the total number of faces by the total dimensions or the total number of features, which in our case is 2914, I guess. Yes. And we can do that by ourselves, but they have already provided, the data is already provided by this data. And if you see, for example, if I pick this data, that is X, and if I say X dot shape, so you will see that. So there are 1288 examples, there are 1288 data points, and each image has, or each data point has around 3000 features, which means 2914 features. Each pixel value is a feature. So these many. So further, we can also have targets. For example, Y is our faces dot target. So if we see the shape of Y, it should be 1288, an array with 1288 entries. Oh, I should call Y dot shape. Y dot shape. It is 1288. Yeah. So each face has a label. For example, if I want to see what's the label for a person with index 100, so I can see the label at 100. So that's the label. So label is 3. And if I want to know what's the name of that, so I can see faces dot target names, and for example Y100. So I will know exactly what's the name. The name is George W. Bush, for example, in this particular case. So the image that is placed at 101 location, which can be accessed by index 100 because the indices start from 0. That person is the ID of the numerical ID of that class is 3, and the string ID of that class is George W. Bush. And we have our data in X. That's our data matrix that contain a lot of data points, and the data is already in numeric form and we just created this numeric form by just flattening the image, because each column or each row is just a row of numbers. We flatten it out and just placed in a matrix, and that is a data matrix. We can do it ourselves because we have this images data available. We can make this X ourselves, but in the given data package, this is available beforehand. Let's plot some of the faces using subplots. Let's do some fancier plotting. What should I do? Let's say let's plot some faces, just some of those. Yeah. So for example, let's say So what I do is, let's say figure and x is, or x is equal to, let's say plt dot subplot. Let me use subplot, let's say 2 by 4. Let's generate a plot with 8 subplots, 2 rows and 8 columns. And let's say for idx and x for idx, let's say x idx, in enumerate ax dot flat. In the flat variant we will be having 8 of those because there are 2 by 4, so when we flat it out we have 8 actually objects. And let's say we have ax idx dot imshow and faces dot images, let's say idx, that's the image. We want to change the color map. For example, C map is, let's say bone. We may also want to get those grids out. There are grids, so just empty the x ticks and y ticks just to get rid of the grid that is coming on the face. Text is equal to, let's say that. We may have, let's label it x label, for example, equals to faces dot target names, and the target is faces dot target idx. So what it should print after this is some faces starting from the idx1, maybe 8 faces, and it will also print the labels of those. So faces dot target idx, it will pick up the label in numeric form, and then we access this particular array, which is the array of strings, and give the index in the numeric form, and it will give us the name. And we just set the x label of the image or plot, this thing. So hopefully it should work. Let's see. Oh, what's the problem? Figure. What's the problem? There is some problem. Illegal argument subplot. I may misspell something. Oh, subplots. It should be subplots. Sorry. Yeah. So now you can see, for example, if I just make a proper viewable zoom level, I've just displayed, for example, 8 faces, and this one is Hugo Chavez, and this is Tony Blair, this is George W. Bush, and all that stuff. And they have multiple images. In this data set, for example, you can see this is also the image of George W. Bush, and this is also image of George W. Bush, and this is also Colin Powell, this is also Colin Powell, and yeah. So each, in this particular data set, there are 7 different persons. Each person has at least 70 faces in the data. Yeah. So yes. So what next? Next is how to build a classification model on that. So before building a classification model, we may have first to split our data to a train test split. So for that, let's build a train test split, or train and validation split. Let's build that. So let's say first we have to import the train test split model selection, import train test split. Yeah, so we did that. I guess it will be imported, and then what we do, we just x train y train, x train x test, y train y test is equal to, let's say, train test split, and let's say x y, our original data, and what should be the test percentage. the test percentage, let's say, is 20%, let's say. So we did that. Now this X train is the data that we should work on, and this Y train are the corresponding labels, and this X test, which should be renamed as X validation, but and this corresponding labels, they will be reserved for model evaluation. Next, what model should we use? Yeah, let's first build. Why not we first build our own model? Let's build a nearest neighbor classifier. Let's build a classifier, or maybe our model that works in a following way. For example, we will pick a test point. And we will see which training point is closest to it and what's the label of that point. And we will just assign this data, this label to that one. And that is called a nearest neighbor classifier. Let's build it. Let's try to build our own model, nearest neighbor classifier. So what we do is, let's say we have a random test point. Let's say we have xt, some test point from the x test. Let's generate some random index. idx is equal to np.random.rand int in the range, for example, y test dot size. That should generate a random index. And let's say xt is our index, xt is our data point for that. Now I want to know what's the label of this. I know the label of this that is there in y-test, but I want my model to actually predict the label of this xt. So one way that I do is I search the nearest neighbor of xt in the training data. So what that means is I want to know what's the point that is closest, what's the face that is closest to it, and what's the label of that face that is closest to it. And that kind of scheme is called nearest neighbor search. So let's do that. For example, what we do is the nearest neighbor index is x train minus xt. Now this broadcasting will happen automatically. You need not to actually resize this xt to just match the dimensions of x train, because there is a broadcasting that is there. So what will happen is this this xt will be subtracted from each training example, and the result will be the subtractions. Now, if xt is closer to something, if this image is xt image is closer to some image, then the subtraction will be very small numbers, or ideally maybe 0. So what we do, we have all these subtractions. We take their squares just to nullify the. We take their squares just to nullify the impact of sign, and then we add to check how similar they are. For example, this, and then we say okay, that's a result. Then we say dot sum, and x is equals 1, because we want to add all these column wise. Now we want to find out where is the minimum. So the minimum, where the minimum is, that's the index of the neighbor, for example. And one way to do that is using argmin function. So return the neighbor, for example. So yes, after that, this nnidx, it will contain the index at which the closest face to xt is located in the training data. And the closeness here is defined by the Euclidean distance or the square distance. Simple. You may have other ways of defining and the actual way should be different. It should not be Euclidean distance, but just to get you a look and feel, how can we build our own model? So now, for example, what we do is we say, okay, y predicted is y train at this particular index, nnidx, and the actual value y true is actually y test at index idx. So let's just print whether they are same or not. Print y true, y predicted. No, the true value was 3 and we predicted 1. That's what happened this time. Let's run it again and see whether next time, because every time it picks a random sample. Now we succeeded. The true value is 5 and we predicted 5. Wow. Let's run it again. It's the same thing. 3, 4. Now we missed. We actually, the actual value was 3 and we predicted 4. So again we missed. And here we succeeded, and so on. So that's our model that we built. Just that is called a nearest neighbor model. Let's see, some of the models are available in this is not a very fancy model. There are great models that are available in, for example, Scikit-learn. Let's explore at least 2 models. One is support vector machines. Let's explore that and apply this face recognition task on there. And then let's explore random forests as well. So let's import, let's do some processing using support vector machine on this real data from, let's say, sklearn.svm, import support vector classifier, and then let's say my model is svc. There are a lot of parameters that I may set here. One parameter is gamma, maybe auto, or one parameter is kernel. There is a regularization parameter called C. There are several parameters. I can go with them. Then what I do is model.fit, and I call x and y, x train and y train. X train, I should not use all the data. X train and y train, and then I have y predicted. Y predicted is m.predict for x test, because I use x train for my training. Now I will evaluate my model using my test data. But I do have my original data as well, original labels. So let me check the performance of this support vector classifier. What's the performance? Let's check it. So for example, accuracy is y predicted minus or equal to, for example, y test. That's the true value. That's y true. That's our predicted. So the accuracy is this, that thing. That's a numpy array dot, for example, sum. Now the sum is there. Then divided by y test dot size, and that's a percentage between, that's a value between 0 and 1. Let's multiply it with 100 to just get a percentage between. So that's just checking how many times you actually guess what that was. How many times you proceed very well. That's accuracy, for example. And let's print the accuracy as, for example, accuracy is, for example, ACC accuracy, and maybe you need a percentage there. Yeah. So it may take a few moments because this training time, it actually depends upon the data. So let's see how better it performs. Oh, the accuracy is very low. This is 47%. That's bad. Whatever we predict is really bad. Accuracy 47% is not acceptable. Maybe we haven't applied any, for example, any pre-processing on this. We might have applied some pre-processing on that. Maybe the dimensionality reduction and stuff like so to get a good accuracy here. But that accuracy is no longer good. Maybe we change certain parameters here. For example, the kernel is RBF, for example. Maybe this helps. Maybe it doesn't. All these are hyperparameters. So let's see whether this RBF kernel helps us or not. It may. No, it doesn't. It doesn't. Yeah, it doesn't. Wow. That's maybe we come up with, let's say, principal component analysis before it, or maybe we build a, for example, a pipeline that actually, let's build a pipeline. Let's build a pipeline, for example. Let's apply some dimensionality reduction before it. So let's import, for example, from Scikit-learn dot decompositions, import, for example, PCA. That is a dimensionality reduction tool. So let's do that. Maybe it helps. So then we can have pipelines, for example. We can build the whole pipeline. For example, from Scikit-learn dot pipeline, import make pipeline, for example. So, oh, something is missing. No module Scikit-learn pipeline. I missed some spelling, I guess. Yeah, here. Yeah, okay. So now what we can do is our, for example, PCA model PCA is, let's say, PCA, let's say with n number of components, components maybe equals to, let's say, 300. Let's say we want to reduce the dimensions from 2914 to just 300. Let's say that's our model. And we may have support vector classifier. Model for SVM is simply SVC with just gamma as auto. And our pipeline model, our main model, that is our pipeline, is just make, let's say, pipeline. We can have more components in this pipeline. What we want to do is first perform PCA, just decrease the dimension to 300, and then apply support vector machines, which is MSV. Yeah. So that's the pipeline. Now the rest of the story is the same. For example, m.fit x train, y train. Then we have all the rest of the story is the same. So let me just copy it from there. We already have fit. Let me copy it from there and we just paste this code here. So now what will happen is the train passes through first PCA and then SVM will be applied. This is just a hope that maybe with this pre-processing, handling this, using this dimensionality reduction, maybe SVM performs better on the given data. Maybe. That's a hope. Let's see. Oh, what's the problem? Make pipeline is not defined. Why not? Oh, the spelling. Always the spelling. So let's see whether we know. We didn't. That's a bad thing. Why we are not performing very well? Why not to change the model? Why not to just go and use random forests? Maybe that is better for this problem. Maybe. Yeah. So let's use random forest. Just because this SVM is not getting me higher than 47. Maybe I can play with this SVM more, but maybe I should just change the model. So let's, for example, go to random forests from Scikit-learn dot ensemble. For example, ensemble import random forest classifier. Okay. Then what? Then my model is simply, let me change this MDL, or model for random forest classifier. That's my model. Oh, what I did here. Oh no, yeah. That's random forest classifier is random forest classifier. And how many individual trees I want in that forest? Estimators equals to, let's say, 30 maybe. Now this is my model. Rest of the story is same. MR dot fit x train y train, and rest of the story is the same. We have to go from there. So for example, this rather than taking this M, now we have MR. So maybe we get something better, maybe, I don't know. And maybe we are stuck the same, or maybe we go lower. So let's run it. Oh, we go higher than 47. Wow, 60. 60 may not be a good number. So there are a lot of things to play with. So yeah, that's real face data. And now, for example, once you have predicted all these labels, you can just get the strings from target underscore names, and just maybe you want to plot these things, maybe you want to label these things and stuff like so. But I guess you understand the general or generic flow of machine learning pipeline. There are a lot of other models. There may be models that you need to build on yourself and stuff like so. There may be, for different data, for example, on another kind of data, maybe another kind of model is working better than, or a complete pipeline may work better than the other and stuff like so. So yeah, I wind up my video here, and for more details of this course, we refer you to enroll our full-fledged course on AI sciences that we explain actually bit by bit each and every detail of it. And if you like this content, do not forget to subscribe our channel, press the notification button, and if you like really, then press the like button and share it with your friends and other people, just to get this thing going and to helping more and more people. So yeah, good luck.